Section 4 is mostly about Kirchhoff's laws, but it starts out with a little bit of terminology that pops up when you talk about these sorts of things. EMF stands for electromotive force. Kind of an unfortunate name, actually. It's misleading. You'd think something called a force would be, a force, but a force would be measured in newtons or possibly pounds. EMF is measured in volts, okay? It's some terminology that dates from a time when people did not choose their words quite so carefully. And actually, I was looking through a textbook once where they didn't even say what EMF stood for. They just tried to avoid that entirely. They just had the letters there because that's what everybody calls it. But the EMF of a battery, for example, or whatever it is that makes the current flow around the circuit, whether it's a battery or a generator or a power supply or whatever, the thing that's pushing the water through the pipes is called a source of EMF, okay? And the EMF of that source is how much energy it gives the charge flowing through it. The energy per unit charge. And energy per unit charge is voltage. So, like if you have a 1.5 volt flashlight battery, its EMF is 1.5 volts. There is a subtle distinct reason for the terminology, I think, is there is a subtle distinction between the voltage between the terminals of a battery and its EMF. If you put a heavy load on a battery, it pulls the voltage down because any battery has a certain amount of resistance in it. The metal plates and the electrolyte in between them and all these materials have resistance just like wires or anything else does. And so what you have between the terminals of a battery is less than the EMF by an amount given by Ohm's law. You've got actually the EMF minus I times R is what you'd have between them. This is the reason why, let's say you need to give your car a jump. It's a 12-volt battery. And, well, let's see not to worry. I've got a whole bunch of calculator batteries in the house. They're 1.5 volts each. I'll just stack up 8 of them. That's 12 volts. Or why be stingy? We'll put 9. That's 13.5 volts. We'll just hook the jumper cables up to that. What do you know? It does not start the car because the starter on a car draws like 100 amps. And you try and pull 100 amps out of those little bitty calculator batteries. Well, the EMF of the battery is still 1.5 volts, but with such a heavy load on it, you're losing practically all of that voltage across the internal resistance, okay? The battery behaves as if it's a pure EMF in series with a pure resistance. It's actually all mixed together, but the EMF provides some voltage, but then you lose some voltage across the resistance. Ohm's law says the more amps through a resistor, the bigger the potential difference. And so anyhow, that's what EMF is. EMF would be the voltage of the battery when it's just sitting on a shelf and you're not drawing any current through it. If you put any kind of a load on it, it'll pull the voltage between the terminals down to less than EMF. If you ever started a car where the headlights are on, you probably noticed the headlights dim down a little bit because, again, you put a load on it, it pulls the voltage down. You're losing a couple of volts across the battery's internal resistance. Kirchhoff's laws. I should probably have the microphone over here. There are 2 of them. who's interested in the history of the subject, I don't remember the exact date, but this was like the 1840s or 50s, I think, somewhere in that general neighborhood. Shortly before the American Civil War, in other words. There are two basic principles that can be used to figure out what's going on in a circuit. Like if I was to ask you some question, like here's a picture of a circuit, tell me how many amps are flowing through that part right there, or something like that. The loop rule is based on conservation of energy, and the point rule is based on conservation of electric charge. But without spending a lot of time explaining the details, what it comes down to is if you follow a closed loop, in other words, a path that brings you back to your starting point. You've got a diagram for some circuit. I don't know if you've ever looked at a schematic for a television or a computer or anything like that, but there's all sorts of transistors and resistors and capacitors and all sorts of branches and wires all over the place. Well, if you start at a certain point and start following some wires, and you maybe pass through some resistors and some other types of devices, and you keep following the wires and eventually get back to your starting point. Assuming that there's a steady state, that somebody hasn't turned something on while you were following the path, if everything is remaining unchanged with time, then all of the increases and decreases in voltage as you go around that path should cancel out when you get back to your starting point. Your starting point was at a certain potential. When you get back there, it should still be at the same potential. And so if you add up the voltages around a complete loop, kind of trace it on the diagram with your finger. As you go around this loop, add up the voltages, you make increases positive and you make decreases negative, and then the total of those voltages should add up to 0. Needless to say, one way of going wrong with this is sign errors, making something positive that should have been negative, or vice versa. So once again, already mentioned this before, but in a battery, the long side of the symbol is the side where the voltage is higher. In a resistor, which end is plus and which end is minus depends on which direction the current flows through it. The upstream end is the higher voltage, or the downstream end is the lower voltage. Current flows from high to low. So, as a simple example, we have here a 1.5 volt battery, like a flashlight battery, and 2 resistors in series. And let's say you come along with a meter. You measure the voltage across the one resistor, and you get 0.9 of a volt. You measure the voltage across the other one, and you get 0.6 of a volt. Notice that if you start here in the lower left-hand corner, just kind of start tracing the path with your finger. And it doesn't matter if you go around clockwise or counterclockwise. That's, flip a coin, doesn't matter. But going around in this direction, the first thing you come to is the battery. And the loop takes you from the low voltage side to the high voltage side. So that's an increase. I made the 1.5 positive. Well, then we continue along. We assume, unless the question tells you something to the contrary, you assume the wires have no resistance, which means that there is no loss of voltage along the wires themselves. Realistically, a small fraction of a volt is probably lost along the wires, but usually you can ignore that. You get to this resistor. The loop I'm following takes me from the upstream end to the downstream end. That's a decrease. So that term gets a minus sign. Same thing with the other resistor. My loop takes me from the high end to the low end. So the change in voltage is negative 0.6. From there I can get back to my starting point. I've completed the loop. Notice that 1.5 minus 0.9 minus 0.6 does in fact equal 0. Okay, add up the voltages around a complete loop, and the total is 0. And that's the basic idea of the point rule, or of the loop rule. Point rule, some books like to call it the junction rule. The point rule is true at any point in a circuit, but it's only useful if you apply it to a junction. A junction being a point where some wires come together. What I've drawn here is supposed to be just a little piece of some much larger circuit. Beyond the edges of the pictures, there's some resistors and maybe batteries and who knows what. And I just didn't bother to draw all of that because that's not the part I care about right now. But there's this junction point where several wires come together. Well, you cannot accumulate electric charge at a point. Therefore, at any point in a circuit that you care to pick, the total current flowing in has to equal the total current flowing out. It's like an intersection between some highways, okay? You've got, right here, you've got 2 coulombs per second flowing through that wire. That's kind of like having 2 cars per minute go down a road. So if you've got a 4 corners, and you got 1 car per minute coming in on this road, and 2 cars per minute coming in on that road, 3 cars per minute coming in on that road. Well, unless there's a junkyard on that corner or a car dealer or something like that, you got to have 6 cars per minute going out on that road. And it's, you know, rate of flow of cars, rate of flow for electric charge. It's the same idea. The rate that current flows into that point has to equal the rate that current flows out. Yes.
Back to the last example there with the circuit, the 9 volt.
Yep. So
like the 0.9 volts, that's the change in.
That's the potential difference between one end of that resistor and the other.
Okay, that's what I thought. The change in potential, so it's losing 9.
Yep. So I'm going to run through an example, and then I'll have you do one, and then we'll probably get into even more trouble on the next page. But for starters, a 10 ohm resistor is in parallel with a 20 ohm resistor. Well, if the question doesn't come with a picture, I would say the first step is to draw a picture before you worry about anything else. You want to be able to label stuff on it and look at what you're dealing with. So here I've got my 1.5 volt battery. And there's a 20 ohm resistor, and doesn't matter which one you draw on top and which one you put under it. Makes no difference which one is where. A 20 ohm resistor and a 10 ohm resistor in parallel across a 1.5 volt EMF. What's the current flowing through the battery? Well, the one I'm going to have you work on in a few minutes is a little simpler than this. In problem number 2, there's only one loop. Here, there is more than one loop, and so there's going to be different amounts of current in different parts of the circuit here, and you need to keep them straight. I usually give them names like I1 and I2 and I3. If you don't like subscripts, you could call them A, B, and C, or X, Y, and Z, or something like that. But let's say that the current flowing through the battery, which is the thing the question actually asks for, let's say that's I1. Well, the current is going to be the same until you reach a junction point. if you've got a road, or to be precise, a road like the thruway where there's no driveways that you can turn off into or anything like that, but if you've got a road with 30 cars per hour going down there, if there's 30 cars per hour going by this point here, there's got to be 30 cars per hour going by that point there. There's nowhere else for them to go until you get to the intersection. Or in a circuit, you call it a junction. At that point there, maybe some of the cars go straight, maybe some of the cars go left. So, I don't know, maybe 20 cars per hour go down this road, maybe 10 cars per hour go down that road. The important thing right now is just to realize that once you get the other side of that intersection, you're going to have different currents than you had back here. So I3, I2, and I'll write it down a little later, but those would be related to each other by the point rule. I1 has to equal I2 plus I3. I know the direction because conventional positive current flows from plus to minus, okay? So I've only got one battery here. Current's going to flow out of the positive current will flow away from the positive terminal of the battery. So it's going to go around the picture in the direction that I've indicated here. Once you get past the junction, once again, it's got to be the same current. That's going to be I3 there, and that'll still be I2 over here. And then at this other junction, they recombine with each other. If this is 20 cars per hour and this is 10 cars per hour, once you dump them both in the same road, you've got 30 cars per hour again. That'll be I1. So I've got everything all labeled and I've named all my currents. And I'm going to start writing loop equations. Of course, the first step in writing a loop equation is to pick your loop. If it's not exactly obvious which loop you should use, well, you can just start. There aren't that many loops. Just pick one by trial and error. By the time you've written enough stuff on your paper, sooner or later, you're going to bumble into the right answer. Sometimes, well, yeah, we already had a trial and error talk earlier today, didn't we? So I started out with going around the bottom half, kind of like this. And again, you can go around clockwise, you can go around counterclockwise. You'll get a valid equation either way. I went around counterclockwise, and I'm going to call that loop number 1. And of course, what I'm actually following is the wires, but I drew it next to the wires because that's where there was space to write that. Should have written this down a minute ago. Find the current through the battery, in other words, find I1. So this is kind of like when I did that other problem earlier today when I made the little list. Here's all my given information, and what am I trying to find? Only this time, instead of a list, I drew a picture. But there's all my given information. There's what I'm looking for. Loop 1. I want to start here in the lower left-hand corner. You can start anywhere, but good a spot as any. I start going along the loop, and the first thing I get to is the battery. And the loop takes me from the low side to the high side. So that's an increase, positive, 1.5 volts. Maybe I'll write down how I know it's positive. Increases are positive, decreases are negative. So I'm tracing this loop with my finger across the battery, and that's an increase of 1.5. continue along the wire, no change in voltage, no change in voltage, no change in voltage. I turn left here at the corner and still no change in voltage. And then I get to the resistor. There'll be a voltage drop across the resistor as the current runs downhill. For now, I'll substitute something in on the next line, but for now I'm just going to write down the voltage across the 20 ohms. I'm going from the upstream end to the downstream end, so that's a decrease, which is why it has a minus sign. So the potential decreases as I cross that resistor, continue along the wires, no change, no change, no change, and I'm back to my starting point. So just those two things have to add up to 0. Well, I'm trying to calculate current. The loop rule doesn't involve current, it involves voltage. But I can substitute Ohm's law in there. That has an I in it. So 1.5 volts minus the voltage across the 20 ohms is equal to the current through the 20 ohms. And again, don't mix up the currents. The current that flows through the 20 ohms has to be the one that you use to calculate the voltage across the 20 ohms. So the current through the 20 ohms times the resistance of the 20 ohms equals the voltage across the 20 ohms, Ohm's law. Well, now I can do a little bit of algebra. .5 equals 20 times I2. I2 is 1.5 divided by 20, which comes out 0.075 of an amp. Trouble is, that's I2. The question asked me for I1. Well, in the end, this turns out to be useful information, but maybe as you bumble through the problem, you don't notice that yet. So you kind of shrug and say, well, let's try again. I'll write an equation for a different loop. This time I need the camera back over here again. Let's go around the outside edge like that. So loop number 2. Let's follow that path and write an equation for it. So again, go tracing along there with your finger or just follow it with your eyes or something. It's going to be similar to the equation that I wrote for loop 1. Once again, you go up 1.5 volts, just like before. Follow the wires, no change in voltage till you get here. And then where I wrote voltage across the 20 ohms, this time it'll be voltage across the 10 ohms. And then you can get back to your starting point with no further change in voltage. So those two things have to add up to 0. So plus 1.5 minus the voltage across the battery minus the voltage across the 10 ohm resistor has to equal 0. And the voltage across the 10 ohm resistor is given by Ohm's law. The current through that resistor is I3. The resistance of that resistor is 10 ohms. Multiply them together, and that's the voltage across that resistor. So I3 is 1.5 divided by 10 ohms. So now we know I3. Again, too bad the question asked for I1, but actually we're almost there. There is no point in writing yet another loop equation. The way you can tell that by looking at the diagram is there's nothing left that we haven't covered following one loop or the other. If you're thinking, well, what if we go around the top half of the picture, the loop that includes the 10 ohms and the 20 ohms, you can write an equation that's true but not useful. The equation you get from that is derivable from the two equations we've already got. So because it covers no new territory, the equation will not be independent of the ones we already. We've exhausted what we can do with the loop rule, but remember that Mr. Kirchhoff, he was probably Herr Kirchhoff actually, I think he was German, but he came up with two principles, not just one. There's the point rule. We haven't used that for anything yet. Well, the point rule is usually useful if you apply it to a junction. So point P over here, where the I1 flows in and I2 and I3 flow, at the junction there. Or the junction over on the left-hand side of the picture would be just as good. Well, let's think of that one. So the point rule applied to point P, the point that I labeled P. Point rule says the total current flowing in equals the total current flowing out. You look at the picture. Flowing toward point P, probably give people one more look at the diagram since I labeled that. There's point P right there, the junction. I1 flows toward it. I2 and I3 flow away from it. So I1 equals I2 plus I3, because I1 flows in, 2 and 3 both flow out. I1 is what I'm looking for, and I happen at this point to know I2 and I3, so I just add them together. 0.075 plus 0.15 So there it is. Question asked, how much current flows through the battery? The answer is 0.225 of an amp is what flows through the battery. Now, as I said, number 2 is not as elaborate as what I just ran through, but that's because number 2 is just kind of a warm-up. If you peek at the next page, things get a little more elaborate later on. But let's take things a step at a time. Find the current flowing in that circuit at the bottom of the page. Probably about time to talk you through this one. So maybe I'll make just a little sketch so I can kind of point at it. Talking. Got a battery there. Got resistor there. And we've got another resistor there. And there's this battery. Resistor. And I'm not going to bother labeling everything on there because you can just look at the picture that came with the question and see how many ohms each one is and that sort of thing. And I should have the camera over here. Now, in number 1, there was only one battery, so it was pretty obvious which way the current is supposed to flow. Out of the positive side of that battery and into the negative side. Here you've got 2 of them. Or I had a guy take a course from me a couple of years ago that he was right. You see, there is this little known thing we have here at the college where senior citizens are allowed to audit courses for free. Okay, if you're beyond a certain age. And if you don't want credit for the course, if you just want to sit there because you're retired and need something to do, you can sign up the course and audit it for. In all the years I've worked here, I've only had 2 people do that, and this guy was one of them. And the thing is, he was a battery guy. I mean, he'd spent his life designing batteries at, I think it was Sandia National Laboratory or someplace like that. And so I'm pointing at something like this and calling that a battery, and he says, like I said, he's perfectly correct. That's not a battery, that's a cell, okay? You're not gonna get 9 volts out of a cell. Depending on exactly what the materials are, you might get 2.5 volts at the most, but so if you've got something like a 9-volt radio battery or a 12-volt car battery, really the way you should be drawing it is like that, where you've got several cells in series that add up to, like a car battery has got 6 cells in it. If it's assuming it's a 12-volt battery. If you look at the little vent things on top, there's 6. Actually, when a battery gets old, I sometimes have been known to pry those off and make sure there's still enough liquid in there. Put a little distilled water in there. Well, anyhow, there's 6 holes. Or if you get an old, like a 6-volt battery, like you'd have in some old tractor, there's 3 cells in that. But that's a footnote. So yes, for 9 volts, I should have drawn several cells for a battery instead of that, but this is quicker, and you can in many ways you can make things easier if you make them just slightly wrong, and I suppose this is one of those cases. So anyhow, now that I've illuminated you on that point, getting back to what I was saying is that with 2 batteries like this, it might not be immediately obvious to you which way the current flows around the circuit. Because if it's going to come out of the positive terminal of this one, it would go around counterclockwise. But if it's going to flow out of the positive terminal of this one, it would go around clockwise. Well, not too surprisingly, the way it works out is the bigger dog wins. If you've got a 3-volt battery trying to push the current in one direction, But a 9-volt battery, trying to make the current flow in the other direction, the 9-volt battery is going to get its way. But let's say that you're not quite that on top of the situation. Then just guess. Okay. Or, maybe it's a more complicated circuit than this, something with several loops in it, and it's not at all obvious whether the current in this branch right here goes the one way or the other way. Make something up. There's only two possible directions. It's either got to go down the wire this way or that way. And if you get it wrong, the current just comes out negative. Okay? So you find out in the end if you guessed wrong. If you're not sure, just give it your best shot. And to illustrate this, I'm going to assume, as I write these equations, that the current flows around the circuit in this direction. And if you were smart, you probably did it the other way around, but I wanted to make the point that getting the direction backwards is harmless. So when in doubt, well, kind of like taking a multiple choice test, when in doubt, guess. If you leave it blank, you know it's wrong. If you guess, it's only probably wrong. So where did I start? I guess I started in the upper right hand. Well, doesn't matter, either corner. Let's say I started up here. And I went around clockwise this time. So the first thing I did is I follow my loop as I encounter the 3-volt battery. I go from low to high, +3. And then the next thing I encounter is this one here is the 100 ohm resistor. According to the direction I chose for the current, I'm going from the high end to the low end. That would be a decrease. So minus the voltage across the 100 ohms. And then I get to the 150 ohm battery. Again, my loop takes me from the high end to the low end. So that's minus the voltage across the 150. So then you come around here and you get to the 9-volt battery. The loop takes you from the high side to the low side. That's a decrease, minus 9 volts. And then from the high side to the low side of that last resistor, 50. That gets me back to my starting point. Those have to add up to 0. The voltage across each resistor is given by Ohm's law. So I've got 3 minus I times 100 ohms. Voltage is equal to I times R. I suppose technically these should be delta V's. Writing all the deltas gets kind of tiresome after a while, but really I should be calling them delta V. 150 ohms times 9, and then one more IR term, I times 50 ohms. Total of all that is 0. Well, then combine the like terms. 3 minus 9 is -6. Combining the 3 I terms, we have 300 times I. 100 plus 150 plus 50 equals 300. So setting it up this way, the current comes out negative 0.02. And again, the reason for the minus sign is because I got it wrong when I assumed the current was going around the circuit in that direction. If I'd been smarter, I would have had these arrows pointing the other way, and then this would have come out positive. But really, what did it hurt? I still found out it was 20 milliamps.
So the answer for one of these questions should pretty much always be positive if you're looking for amp.
Well, any plus or minus sign gets into the direction that it's flowing in. But yeah, if the question is just simply, how big is the current? You know, if you put a meter in the circuit right there, how many amps does that meter read? That's going to be a positive number that's asking for. Okay. So for anyone who needs help with my handwriting, that says that the minus sign is because the direction of the current is opposite of what I assumed. Just a little footnote. Notice that in a series circuit, that all of this follows from the point rule. These are things I think I had mentioned before, but I just asserted them without any sort of explanation. But these things follow from the point rule. If you've got a parallel circuit, then apply the point rule to the junction, and the total current is equal to the sum of the currents in each branch. In a series circuit, you've got the same current everywhere, like this one you just did. The current through this resistor is the same as the current through that resistor. For that matter, the batteries all have the same current through them. So maybe I shouldn't have erased that yet, because this one maybe resembles that. Well, there's still half of it over there. But this one resembles the one that I did earlier a little more. This time, you've got two loops, and you need to find the current. Well, just this one here, number one, it only asked for I1, but along the way I found I2 and I3. This one here asks for all of them. So it's going to be pretty similar to number one. Try and see how you do. Well, here goes number three then. So as I said, you can just start writing random loop equations if you don't really have any sense of where you're trying to go. Sooner or later, you'll bumble into the right thing. But I think what works out fairly well is if one of your loops is if you go around the outside edge of the picture, kind of like this. You've got the 10 volts at the upper left and 50 ohms. And you don't have to worry about getting the directions backward this time because the nice person who wrote the question labeled that for you. So that kind of gets you out of worrying about that. It shows I3 flowing in that direction. The middle, you know, the 30 ohms that's in the middle there is not part of the loop I'm following, so I'm just not going to draw it. So based on this loop, I can say that the voltage across the 50-volt battery plus, because see, going around like this, then go through that 50 ohms, I'm going from, well, actually that would be negative. Should probably have a minus sign there. I'm going from the high to the low end, minus the number of volts across the 50 ohm resistor. And then I'm going from the high to the low side on this battery. So that's going to be minus voltage across the 10-volt battery. Those three voltages have to add up to 0. The loop rule says add up the voltages around a closed loop. One of the mistakes I see is people throwing things in here that are not voltages. They'll have just 50 ohms without multiplying it by a current, or they'll have some number of amps without multiplying it by a number of ohms. So summation of the voltages equals 0. Each term should have volts for its unit. So the voltage across a 50-volt battery is 50 volts. The voltage across the resistor is given by Ohm's law. And the voltage across the 10 ohms, or I'm sorry, the voltage across the 10-volt battery is 10 volts. I3 is the current flowing through the 50 ohms. So it's I3 that belongs there, not I1 or I2. Well, this is going to work out. Just one variable in the equation. 50 minus 10 is 40. And if I add the 50 I3 to both sides, kind of doing two things at once here to save a little bit of time, added the 50 I3 to both sides, also combined the 50 minus 10 into a 40. Finally, divide through by 50. Eighth of an amp. Next. I went with the bottom half of the circuit for my next loop. You've got the 50 volts down on the bottom. And there's this 30 ohms that's in the middle. Current flowing through that is I2. Based on that loop, if you start off here, start going around like this, first thing that happens is you go from the low to the high side of the battery. So that's an increase. It gets a plus sign, 50 volts. Come along here, no change along the wires till you get to the resistor. You're going from the upstream end to the downstream end. That's a decrease, so it gets a minus sign. Voltage across a resistor is given by Ohm's law, I times R, where R is 30 ohms, and the current through that resistor is I2. And from there, you can get back to your starting point. So you do a little bit of algebra with that equation and 1.67 amps. And then just like I said when I was going over number 1, this exhausts everything you can get from the loop rule. If you try to write a third loop equation, it will not be independent of the 2 equations you've already got. You can tell because it doesn't cover any new territory that wasn't already included in one of the other loops. But there's the point rule. If you look at the junction in the middle of the right-hand side of the picture, I1 flows toward that point. I2 and I3 both flow away from it. Total in equals total out. So I1 equals I2 plus I3. And that's how you finish off that one. And now, that's probably enough progress. Why don't we leave it here for today? If it was 5 minutes earlier, I'd say let's go on into the next problem, but I've probably given you enough of a headache already.